right, here we go. Welcome to chemistry lesson 5.03. You notice we skipped 5.02. That's because we did that one in class. We talked about reactivity in class. And let's kind of recap what we've said in 501 and 502. Also talk about what the purpose of this video is going to be. So you'll notice at the top, my title here is Periodic Trends. We have trends in behavior, and we saw that with reactivity in the last lesson. And we keep attributing a lot of that behavior as we go from left to right on the fact that this side of the table, so over here, we want to lose electrons. In order to fulfill the octet rule, actually I need to be careful because I have non-main group elements selected there. So I should have just done these two columns to be most accurate. Let me just white that out. And over here, so these guys are also trying to lose. When we get to carbon, they're a little bit on the other side, and these three columns or groups are trying to gain electrons. So this column is losing one electron, this is losing two, this is losing three. Over here, we're trying to gain one, gain two, gain three. And that correlates to the ions that we're going to form, but this really does contribute to our behavior. So we have four more trends to talk about. Reactivity is one of them, and we're going to talk about number 2 and number 3 in this video. So the first one we're going to talk about is ionization energy. And we defined those, you looked up some definitions for me on another page. And the definition for ionization energy is the energy required, E-N-E-R-G-Y, required to remove an electron. And we know when we remove an electron, we end up with a charge and we form an ion, so it's called ionization energy. So to sum it up, a lower ionization energy, and IE will be the abbreviation for that, is an element that easily loses an electron. If you have a higher ionization energy, you really hang on to your electrons. So higher ionization energy, it's very difficult to lose an electron. And we have to talk about the trends both from side to side and from top to bottom. So let's pick two elements here. Let's look at, and I'm going to grab my purple marker. So let's compare left to right to start with. So let's look at, how about sodium and chlorine? So I'm going to highlight sodium here, and I'm going to highlight chlorine over here. Now you'll notice I didn't come all the way out to the side. Why would these guys not be something I would consider? Well, these are the noble gases, and remember they have an octet, so their ionization energy is through the roof. They do not want to either give up or gain an electron because they already have 8. So over here I'm looking at sodium, Na, and over here I'm looking at chlorine, Cl. So if we look at chlorine, how many electrons does chlorine have to gain to get an octet? Did you say 1? So chlorine needs to gain 1 electron. And how many electrons does sodium have to lose to form an ion? Here we're talking about losing 1 electron. So if the ionization energy is the energy required to remove an electron, is it going to be very tough to convince sodium to give up an electron? No, it's trying to do that anyways. So it's easily losing an electron. That's going to give it a really low ionization energy. So you don't have to convince it. It's like, hey, it's like the garbage. You're trying to get someone to take it away anyways. Over here, chlorine's trying to gain 1 electron. So if you're talking about trying to take an electron away from chlorine, it's already hanging on to the 7 it has, and it wants to gain one more. So is it going to be difficult to take an electron away from chlorine? Absolutely. What happens as we go from left to right? And let's put a little note in here about our arrows. So arrows always point from low to high. So we've got sodium here, and we're going to increase in ionization energy. Oops, and you know what? I don't want to put the, actually, you know what I do? No, I said that incorrectly because it's some of the other traits, which be careful incorporating the Nobel gases. But no, it's going to go up to the Nobel gases because they really don't want to lose an electron. They already have 8. So not only do you need to understand that ionization energy increases as you go from left to right, you have to understand why, and the why comes down to this. So you have to understand the tendencies, and we're usually talking about main group, but it's true for the intertransition metals as well. So for example, here we have nickel. Nickel is going to have a higher ionization energy than sodium. Well, that takes care of half, but we also have to consider top to bottom. So we have sodium here, and let's compare sodium to, let's do rubidium. Actually, you know what? I'm going to do lithium, and I'm going to do rubidium. So let's do lithium in orange. And I want to write out the electron configuration for lithium. I'm going to bring that a little further out. And let's do rubidium, 3 up in, let me pick a different color. We do light blue. How about light purple? All right, so that's going to be rubidium. All right, I'm going to let you pause the video, and I'd like you to write out the electron configuration for lithium, and I'd like you to write out the electron configuration for rubidium. So pause it here. All right, we're back. Hopefully you wrote 1s2, 2s1 for lithium. Rubidium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, I'm running out of room, 5s1. Now they both have an S1. They both end with S1. So there's one electron in the valence. And remember, we're always talking about, I should probably specify on these definitions, a valence electron. So it's not these inner shell electrons. We're going to kind of ignore these guys. They do factor into behavior. So this should be a valence electron. Valence electron. So put that into your definition. So what happens? Who is it going to be easier to pull an electron away from, lithium or rubidium? Well, here, to understand the trend from top to bottom, we have to look at the attraction. So I'm going to circle my valence electron. I have one valence electron here. This has got a -1 charge, and I've got one valence electron here, and that's got a -1 charge. And then in the nucleus, I have a positive charge. So I've got these positive neutrons. What happens when we put a positive charge next to a negative charge? Opposites attract. These two charges are attracting each other, and these charges are attracting each other. But one of the things that's true about electrical charge is that attraction varies with proximity. The closer two charges are together, the stronger they attract. And you might have seen this with magnets. If you have magnets far apart, it's a decently strong magnet. They really don't do too much. But if you get them close together, all of a sudden they'll snap together. So we have that same phenomenon going on here. The positive nucleus of lithium is really holding on tightly to this valence electron. But look at rubidium nucleus. It's got all of these inner shell electrons in between it and the valence. So it's hard for this nucleus to hang on to this valence electron. So because of that, hanging on harder, more difficult to lose an electron, we have a higher ionization energy. Down here at rubidium, it's going to lose that electron more easily because the nucleus can't pull on it as strongly. So what we have happening with ionization energy from the top to the bottom of the table is this. So ionization energy increases as you go up the table and as you go to the right. And you'll need to have that memorized, but not only the trend, also the why. You have to understand why. So let's just write a little something down about that. So the greater the distance, the weaker the pull on the valence electrons. And remember, we abbreviate valence electrons as VE. The shorter the distance, the stronger the pull. One of the things that you'll do are practice problems, or you might see on the test is a problem like this. So let's throw a practice problem. Let me give you 3 elements. Put the following elements in order of decreasing ionization energy. And let's do nickel, strontium, and nitrogen. So this problem requires you to assimilate quite a bit of information, and I'm going to outline them in orange. So strontium is going to be here. It's right next to rubidium. I'm going to pick a different color beside. Well, yeah, it's okay. So here's strontium. I'll fill them in. Nickel is an intertransition metal. It's 3 over. It's here. Then nitrogen is here. So the first thing I have to do is locate these guys. The second thing is I have to understand if I'm decreasing, I want the strongest, so I want to go from the strongest to the weakest. So I have to read the problem right. So I want the strongest to the weakest. The next thing I need to do is I need to remember what my trends are, and I need to remember that I increase as I go up and as I go to the right. So the element that is the furthest up and to the right is nitrogen. So nitrogen would come first. And then we're going to go down to nickel. And then I'm going to come, so as I come to the, I'm going to decrease as I go to my left and as I go down. So strontium would be the weakest. And that's a common problem of this type. Now, we have a second trend I want to talk about in this video, but luckily, it's not going to take nearly as long. So I'm going to pull my camera down. The next one I want to talk about is electron affinity. And the reason it's not going to take us as long to talk about this, I'll explain. The definition is the energy that's released. Electron affinity is the energy released when an electron is added so higher or lower, let's start with higher. Higher electron affinity means that an element easily accepts an electron, and lower electron affinity does not easily accept an electron. Well, electron affinity and ionization energy are kind of mirror images. So let's say you've got a fella or a gal you've got a crush on. You might say, boy, I really like Tommy, or I really like Susie. So if you talk about that, you could also say, boy, I really don't dislike so-and-so. And you're saying the same thing. You're just saying one is a positive and one is a negative. And that's what ionization and electron affinity are like. They're kind of talking about the same thing in different terms. So you're saying on one hand, how hard is it to pull something off? On the other hand, you're saying how hard is it to add something? So because of that, we have the same trends for the exact same reasons. So we're going to increase as we go up the table, or we're going to increase as we come across the table, because now, but here I have to be careful because the Nobel gases do not, no, actually, I'm still okay. Apologize. Yep. And I said this backwards. Okay, I should have stopped while I was ahead. So yeah, we're going to go up to, because the Nobel gases are not easily going to accept an electron. So, and I probably should not include the rare earth metals down there. So think about, again, we talked up in the top, we talked about rubidium down here, and rubidium is desperately, let me outline that in light purple again, is desperately trying to get rid of that electron. So it is going to have a really low electron affinity. It is not going to want to accept electrons. Versus over here with chlorine, where my purple marker go? Chlorine is only needs one more electron, so it's going to have a really high electron affinity. It's going to easily accept an electron. It's going to release a boatload of energy. Think about throwing a party. If you're going to win the lottery and you only need one more number, when you get that number, you're going to throw a big party, and that's what chlorine does, except it throws out a whole lot of energy because it gets its octet. Over here, rubidium doesn't want electrons, it's trying to lose electrons. And we have the same trends from the top to the bottom. So if I look up here at lithium, that nucleus, the valence electrons are really close to the nucleus, and so there's a stronger pull. That's going to create a higher attraction and a higher electron affinity, versus down here we've got a really weak nuclear pull. So again, we have the same trend for the same reasons, and we're kind of saying the same thing. So if you had a dozen donuts and you ate 7, you had 12 donuts and you ate 7, you could say, I ate 7 donuts, I have 4 donuts left. That's saying the same thing, it's just the mirror image of it. So again, it's not enough just to memorize these trends, you also have to understand why. So you have to know the why of it. So if you have questions, we will be doing some work on this in class. Otherwise, that's all we've got for now. Thanks for watching and have a good day.